Let's apply De Morgan's laws to conjunctions and disjunctions. So, we've got a few things to talk about. What are De Morgan's laws? And what are conjunctions and disjunctions? If you don't know that, this is going to be difficult. So let's start with disjunctions and conjunctions. Now, the conjunction is an and statement. So we often in logic or truth tables will talk about P and Q. So I always think of this symbol as an A without the line, right? That helps me remember what the and statement looks like. Now a disjunction is an or statement. So we would say P or Q. So the symbol looks more like a V. Okay, so those are conjunctions, disjunctions. De Morgan's laws. Now, De Morgan's laws basically say that we can take negations or distributing negations across conjunctions and disjunctions, and each law, there are two, show equivalent statements. Okay, so we're playing with negations along with conjunctions and disjunctions to show equivalent statements. So it's one of those things of, oh, if I have this, I know by De Morgan's laws that this statement is also true, right? We're just looking at two congruent or equivalent statements. So De Morgan's laws, what are they? Well, the first one. The first one says that if we have not P and Q, conjunction, that if and only if not P or not Q. So De Morgan's law says these two, the left and the right side of this biconditional, are congruent or are equivalent. So basically, it's like we're distributing that negation and flipping the symbol. Okay. The second one says not P or Q, disjunction, if and only if, not P and not Q. Okay, now look at these. Really look and pay attention. So when we think about distributing the negation from that last line, right? The negation going to everything on the inside. If we think about that, look at the difference between the left sides and the right side. So we distribute the negation across and we flip the signs. So that's kind of the key of De Morgan's laws. Now, let's show De Morgan's laws are true by creating a truth table. So if we think about what we're going to need P, Q, not P, and not Q. Let's start there. All right, so we know we have two items, P and Q, so we have 4 lines. So I've given us P, Q, not P, and not Q. Now, if we think about the first one, so let's go with, let me see, how many lines am I going to need? I believe I'm going to need 6. So 1, 2, 3, 4, 5, 6. Whew, that fills up my whole piece. Okay, so I'm just going to write it kind of here in the middle, and then we are at the end, and then we'll just do it later. So if we're looking at the first one being not P and Q, if and only if, not P or not Q. Okay, so we're going to do this one first. We need to talk about P and Q. Okay, so let's do that first. So if we have P and Q, well, that means they both have to be true. So I'm looking at P and Q, both true. True, false, false, false. So now if I'm thinking not P and Q, well, I just switch them. False, true, true, true. So now I can compare, right? I can compare that to the right side of not P or not Q. So let's go ahead and do the right side. Let's change the color and do not P. You know what? Let's get rid of these. Okay. Not P or not Q. Now, so I'm looking at the not P, not Q lines. Or means only one of them has to be true. So, not P, not Q. Oh, those are both false here. False, true, true, false, true, true. Y'all, when you're looking now to compare these two, notice what you see. They're false, true, true, true. That shows the first De Morgan's law is true because the left side and the right side, the if and only if, they have identical truth table statements. Okay, now let's look at the other one. Okay, so law 2 is not P or Q. Okay, so we're going to start with P or Q. Okay, so P and Q, one of them has to be true. True, 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 false. Well, when it becomes not P or Q, we flip it. False, 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 true. Great. So that's the left side. This is one that we're comparing. Now let's look at not P and not Q. So now we're looking at the nots, and because it's an and, a conjunction, both have to be true. False, 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 true, false, true, false, true, true. And again, when you compare the two sides of this biconditional, they have the same lines in a truth table. So this shows the second De Morgan law to be true based off of a truth table. Okay, now how do you use this? Sorry, it took us a bit to get there. But using De Morgan's laws, what's an equivalent statement? Well, notice what you have. You have a negation on the outside. So we distribute that, not R, not M, and we flip the sign, right? So instead of having not R or M, we have not R and not M. And that is an equivalent based off of De Morgan's laws. Now, one other thing I want to throw out is that we could have, it doesn't matter what the letters are, we could have a negation inside. So to do this, we'd say, okay, well, again, distribute the negation. Well, not M is M and not T, and flip it, M or not T. Same idea, right, of being equivalent based off of De Morgan's laws.